Hello dear student, welcome again to the tetrahedron chemistry classes. So guys, in today's lecture I am going to discuss a very important reducing agent, lithium aluminium hydride, LAH. The short form is, abbreviation is your LAH, and the formula is LiAlH4. Okay, though I have already uploaded two lectures on the reducing agents. First was your dibal and second was your I think it was sodium borohydride, right? So in that particular series today I am going to take this lithium aluminium hydride in the pretty much detail. What are the different applications of this very special reducing agent, okay, and how we can prepare it, and what are the important functional groups which can be reduced by this lithium aluminium hydride. Okay, so let's start the video. See, this is the formula, lithium aluminium hydride, and it's a hydride donor. That means it will liberate H negative ion to the compound, to the other compound, right? And since it is the hydride donor, that means H negative species. So what I can do, I can write H here, negative here, right? So this is your hydride ion, and this lithium aluminium hydride can donate this hydride ion. So it's a nucleophilic reagent. Okay, because it is negatively charged species, it can attack on the electrophilic carbon. So it's a nucleophilic species, right? And this hydride ion which comes from the lithium aluminium hydride, it will always attack on the electrophilic carbon, and that electrophilic carbon is generally present in the carbonyl compound, right? You know the carbonyl compounds, especially your aldehydes and the ketones. And you know this carbonyl group is also present in the acids and the acid derivatives. So all these compounds, carbonyl compounds, acid and acid derivatives, can be reduced very efficiently with the help of this lithium aluminium hydride. However, the same work can be done by the sodium borohydride as well, but sodium borohydride cannot reduce any acid and the acid derivatives generally. So for the reduction of these acid and the acid derivatives, we'll use this lithium aluminium hydride. And along with this carbonyl compound, cyanides, basically here cyanides, which are generally known as the nitriles. Nitrile compounds can also be reduced with the help of this lithium aluminium hydride. And the physical state of this lithium aluminium hydride is the gray white solid. How we can prepare this gray white solid of lithium aluminium hydride? So for this we need to take this lithium hydride, four equivalents of this, and we can react these four equivalents with the aluminium chloride. So generally what we do actually, we gradually add your limited quantity of the aluminium chloride to a thin paste of the lithium hydride. So we'll make a thin paste of this. So what I can do, I can write here thin paste. So we'll make a thin paste of aluminium hydride, and to this we'll add this slowly. We'll add the limited quantity of the aluminium chloride to it. See, we cannot add the aluminium chloride in excess. When you add the aluminium chloride in excess to the lithium hydride, then your lithium aluminium hydride will not be the product. The product will be something else like lithium chloride. Okay, see, so this is how you can prepare this one. So to that okay, and this is your, say, lithium aluminium hydride, and this is your lithium chloride. It is not carbon, I'm sorry, this is your lithium chloride. So it is the precipitate of the lithium chloride. So what we will do, we'll get this mixture, right, with the help of this reaction. Basically when we do this reaction of lithium hydride with the aluminium chloride, we get this particular mixture, and in this mixture your lithium chloride is the precipitate. We can filter this precipitate and we can discard this, and to this particular filtrate, what we can do, this filtrate will have actually your lithium aluminium hydride. Okay, so what we will do, we will evaporate this filtrate in absence of carbon dioxide and air, right? Because this lithium aluminium chloride quickly react with the carbon dioxide as well as air. So in the absence of the air and the carbon dioxide, we will evaporate that filtrate, and when all the water goes out, then you left with this gray white solid, which is your lithium aluminium hydride. So this is the method of the preparation. Okay, now, right, so what are the functions of this lithium aluminum hydride? So I have summarized all the functions of this lithium aluminum hydride, and basically it is a very strong reducing agent. Please remember, it's a very strong reducing agent, much stronger than the sodium borohydride, please remember. And the carbonyl chemistry is the very important chemistry in the synthetic chemistry and also in the natural systems. So it is generally used for the reduction of the carbonyl compounds, and the variety of the questions comes from this particular topic in the CSIR net examination, as well as in the GATE and in the IID JEE examination, or say in your NEET examination. So we'll mainly focus our study on the reduction of the carbonyl compounds with the help of the lithium aluminum hydride. So you see the aldehydes, we are having the ketones, then your acids, acid derivatives like esters, right? So these are generally reduced by the lithium aluminum hydride. And first we will do the reduction, and after the reduction the protic workup will take place. So first hydrogen actually comes from the your lithium aluminum hydride, and second hydrogen comes from the solvent actually, right? And it is proved by the deuterated, when we use the deuterated solvent. So it is proved that the one hydrogen comes from the solvent as well, right? So whenever you do such reductions, you need either ether or the tetrahydrofuran. And all these aldehyde, ketone, acid derivatives, whether your epoxides or ozonides, they all can be converted into the alcohols. So now it is very clear to you, whenever you see lithium aluminum hydride along with these functionalities, then quickly in your mind you will remind that okay, this we have learned, and these all can be converted into the alcohols with the help of these reagents. So this is very important. And next you see your amides, your RN3, right, and your nitro compounds, aliphatic nitro compounds, your nitrides, that is cyanides, right, your oximes, anylides, they all can be reduced with the help of the LAH, that is lithium aluminum hydride, to the amines, right? If you have the aromatic nitro compounds, then aromatic nitro compounds on the reduction with the help of this lithium aluminum hydride will convert into the azobenzene, right? While your aliphatic nitro compounds will convert into the amines, and aromatic nitro compounds will be converted into the azobenzene, right? So with the help of this lithium aluminum hydride. If you have the sulfonyl chloride, then with the help of this lithium aluminum hydride, we can reduce the sulfonyl chloride to the thiols, okay, and your sulfoxides to the thioethers, and halides we can convert, or we can reduce with the help of the lithium aluminum hydrides to the parent hydrocarbons, right? So this slide is very important for you, very important, okay. Right, as I already told you, the carbonyl chemistry is the very important chemistry. So we will give much attention to the reduction of the carbonyl compounds with the help of the reducing agent. We will see the mechanism as well, okay. And then we will do the variety of the problems, which includes the problems which also gives you the practice of your stereochemistry as well. Okay, so we will start the reduction of the carbonyl compounds. So how we can reduce the carbonyl compounds with the help of this lithium aluminum hydride. So I am writing the general reaction here. So in general, 4 of the carbonyl compounds, this is the general formula for the ketone, right? 4 molecules of the ketone will be reduced by the 1 molecule of the lithium aluminum hydride, okay. So what it will form? First it will form here R2, which are present here, the CHO type of the compound, and 4 of this will take, right? And then your aluminium is here, and we will put this species in the bracket, and your lithium, right? So this salt is present, and then we'll do the protic workup for this one. Heading here, protic workup. I hope you know what is the protic workup in the organic chemistry or in the synthesis, okay. That means reaction with the dilute acid, protic workup. Sometimes you can write H positive as well, okay. So when you do this, you'll get 4 of alcohol, 4 of R2 CHOH, this is your main product, and your lithium hydroxide will be eliminated from here along with the aluminium hydroxide. So this is the general reaction. Okay. And so the very important thing or the advantage of using lithium aluminium hydride as reducing agent is that we can reduce 4 moles of the uh, carbonyl compounds to the alcohols with the help of the only 1 mole of your lithium aluminium hydride. This is the very important advantage. And another advantage is that generally this lithium aluminium hydride cannot actually reduce your double bond, isolated double bond. But if your double bond is in conjugation with the phenyl ring, then of course you can reduce that double bond as well. We'll see the example of this later on. Okay, so this is the general reaction. Now quickly we'll see the mechanism, actually how the mechanism goes for this one. So for to explain the mechanism I need some space, so you can take the snapshot of this. I am removing this equation. Okay, but you should remember that you should remember that point that removing this. Okay, I'm removing this. Now the mechanism of the reaction. So how the mechanism goes? So I'm writing here mechanism. I'm writing mechanism. Very simple mechanism is there. So this is your aluminium connected with the 4 hydrogens. So I'm writing 4 hydrogens here. Okay, and of course your aluminium will have the negative sign over there. So I'm putting negative here, and of course its counter ion, lithium ion, will also be there. This is positive. Okay, and then you will take your ketone molecule. Say this is your R. This is carbon, double bond oxygen, right? And this is R as well. And please remember, this is your electrophilic carbon. This is your electrophilic carbon. I hope you know. I hope you have an idea why actually this carbon is the electrophilic carbon, right? Because it is a it will create the positive center actually, right? Okay, I hope you know why it is the electrophilic carbon, because you know this oxygen is here, and when this electron pair will be shifted onto this oxygen atom, this carbon becomes the positively charged. Okay, that's why it is electrophilic in nature, and any electrophile any nucleophile can attack over it. Okay, so what will happen in that in here, you see one of the hydrogen along with its electron pair will attack onto this carbon atom, and this electron pair will shift here. Okay, and then you will have your first species, and what will be the product? Your R was there, and this is your carbon, and another alkyl group was there, and this is the hydrogen which is coming from the aluminium, right? Aluminium hydride from here. Okay, and the remaining part of this is what? This oxygen will become negatively charged. You know, when it will shift here, it will get negatively charged. So this negative is over there, and you are having AlH3. Of course, this part would be negatively charged, and lithium positive will also be there. So this is the reaction. Okay, and then what you can do, see, it's quite simple to see here, because this aluminium is having 4 hydrogens. Okay, 1 hydrogen is used for this one particular molecule of your ketone. That means the second hydrogen will do the same reaction with this one, and then third reaction, that third hydrogen will do the same thing, as well as the fourth hydrogen will do the same thing as well. R2 C double bond O. This is my ketone. See, this ketone I have written here again. So what will happen in the next step? What will happen? One of the hydrogen from here, okay, one of the hydrogen will attack onto this one, and this will shift there, and you will have your another very important species, R, carbon, R. Now I can write CH here, okay, and oxygen here, and you know these are the 2 such things here, and remaining is what? Your aluminium H2. Now this is Li, positive, this is negative. It is quite clear. Earlier, this aluminium was connected with the 4 hydrogen. In the second step, it is connected with the 3 hydrogens. Now, when you form this particular species, this will connected with the 2 hydrogen. Okay. So, what will happen in the next step? Again, the same reaction will happen. This hydrogen will again attack onto this one, and this will come here. So, what would be your next species? Next species would be, and now you left with the last hydrogen. So, what your last, last hydrogen with your aluminium. So, what you can do, will attack onto this one, and this will come here, and you are having another species, and that species would look like this. Is how actually we do the reaction. And in the last step, we do the protic workup. Okay, dilute acid you will take for this one, and then you will form your product, and your product would be here. So what you have seen here, or what you have learned, that means one of the lithium aluminium hydride can reduce 1, 2, 3 and 4 molecules of the carbonyl compounds. It is very, very important. However, a very important point is that if you see the rate of the reaction, okay, so the first step would be the slower one, a slow step rather, not slower, the slower one, and the second step is the slower one again, okay, and you see the last step would be the slowest one. That means the rate of the reaction keeps on decreasing when you have your this alkoxy group here. Why this actually happens? This alkoxy group actually is your electron withdrawing group, right? It shows the negative I effect, okay, and that alkoxy group actually opposes the removal of the hydride ion from the species. That's why the rate becomes slower and slower. Say this is my reaction number 1, and say this is my CH3 and this is CH2 and 5 of the CH2 like that, and this is your aldehyde. Okay, so what you will do with aldehyde, you will take your lithium aluminium hydride. This is in the first step. In the second step, you will do the protic workup, and you will take in that case ether, or you can say THF. So what will happen? Your carbonyl compound will be reduced into the alcohol. So your product would be CH3, CH2 5 times, and then you are having CH2OH. And please remember one thing. See, earlier one this was CH, now it has become CH2, right? And this actually hydrogen comes from this hydrogen especially, this comes from the reagent. This comes from the reagent, and the reagent is lithium aluminium hydride. Okay, and this hydrogens comes from the dilute acid, that will protic workup, or you can say the solvent. Okay, so this is how the reaction goes. And similarly, the same reaction you can check here. Say for example, you are having ketone CH3, CH2, C double bond O, CH3, and you do the same reaction, right? First you will take your lithium aluminium hydride, LAH I am writing, and second you will do the protic workup, and if you take either THF tetrahydrofuran or your diethyl ether, and then you will have your alcohol, which is your CH3, CH2. This is your CH, and this hydrogen is coming from the lithium aluminium hydride, and then this would become OH, and this hydrogen is coming from the your protic workup, right? This has been proved by the experiment as well, right? If you take the uh, deuterated acid in case of the protic workup, then deuterium would be here. So this is coming from there. Okay, and variety of reactions are there. Now suppose these are the aldehyde and the ketones. Say you are having this compound CH3, C double bond O, CH2, So this is your active methylene compound, C double bond O, OC2H5. This is your active methylene compound, and you can do the same reaction. You can take your LAH, I am writing lithium aluminium hydride, and of course you will do the protic workup as well, protic workup, or you can write H positive over there. Okay, so you will have your CH3, and then you are having CHOH. This carbonyl group will be reduced into the alcohol, and then CH2 was there, and then you are having CH2OH. Okay, and this will remove as alcohol from here. Okay, so you are having this one, this species is there. So these are the very simple reactions, but you know, in the examination you will never have very simple examination, very simple questions. Okay, so what we can do, this is very important. This is CH3, your compound is CH3, CH, double bond CH, and then CH2OH. And again, don't forget the important thing, one hydrogen, this hydrogen is coming from the lithium aluminium hydride, and this hydrogen is coming from the solvent, right, this one. Okay, and if you want to know the name of this compound, I hope you are familiar with this molecule. This is croton aldehyde. This compound is croton aldehyde. So this is your croton alcohol, this is your croton alcohol. And the very important thing which you are noticing here, this double bond is not reduced by the lithium aluminium hydride, and when this double bond is non-conjugated with the phenyl group, this cannot be reduced with this lithium aluminium hydride. However, if you replace this CH3 with the phenyl ring, then this will come in the conjugation with this one, and then it can be reduced very easily. 35 degrees centigrade. This reaction will happen at the 35 degrees centigrade. Okay. Now you can see this double bond, this particular double bond will also gets reduced. How? So this is where it is a very important feature. When your double bond is in the conjugation with this one, then it can be very easily reduced. Okay, please remember this point. Okay, and see what will happen actually, why actually this happens, this double bond gets reduced. See, due to this conjugation or the mesomeric effect, you see here, this double bond also gets polarized. So one electrophilic center will be produced onto this carbon atom, and then your nucleophile from this LH can attack onto this one. The reason is this one, very important. If you do this reaction at minus 10 degrees centigrade, then in that case your double bond will remain intact in the product as well. That means it cannot be reduced, this double bond cannot be reduced by the lithium aluminium hydride if the temperature of the reaction is very low. Very important rule. Okay, right, I'll write the reaction for this at 35 degrees centigrade temperature, where you are also reducing this particular double bond to the alkane part. Okay, phenyl ring, this is your benzene ring. Okay, here like that, Li ALH3 I am writing, and one of the hydrogen I am writing in that manner because I need this hydrogen for my reaction. Okay, so what will happen, you see, this hydrogen will attack onto this alpha carbon. Please remember, it will attack on the alpha carbon. I hope you know what is the alpha and the beta carbon. This is your carbonyl carbon, which is the main functionality. This is your alpha carbon, this is your beta carbon. So this hydride will attack onto this alpha carbon first. Okay, and when it will attack onto this one, you will have your species, and that species would look like, this is my pH, which is phenyl. Okay, and then you see this is negative here. What will happen actually, you see, when this hydrogen along with this electron pair, that means as hydride when it is attacking onto this one, so this electron pair will shift over there. So I am shifting this electron pair onto this carbon atom, so it will get a negative sign here, this negative sign. Please remember, it is very, very important. Okay, and then you see this will become CH2. I am writing like that. Okay, and this species is having only one hydrogen. There is no problem in that. And this is your carbonyl functionality. This is H. I hope this is quite clear to you. Okay. Now you see, since this is the negatively charged species, so this will have its positive counterpart as well. So its positive counterpart is what actually? You see, your, sorry, change the color. This is your Li, Al, H3 now. Okay. This is positive, this is negative. So this negative will attack onto this aluminium, right? And what, I'm sorry, I made a mistake. This negative is not there because I have already put it this negative here, right? This will remain as such. Okay, so this negative will attack onto this aluminium connected with the aluminium, and that aluminium is having 1, 2 and 3 hydrogen. Of course your lithium would also be there as positive species, and this negative is over there. Okay, now what will happen? One of the hydride actually will attack onto this carbon, okay, electrophilic carbon, and this will get shifted over there, and then you are having your next species O negative. Please remember, this is your O negative. Okay, and this was your hydrogen, and one hydrogen is coming by the attack. Okay, and this was your pH, and it was now connected with this aluminium, and that aluminium is having only 2 of the hydrogens now. Okay, I hope this is quite clear to you. Now what will happen in the next step? Now this negative will attack onto this aluminium, and this will attack onto the aluminium. You have a 5-membered ring, and you see in this picture here, just after the oxygen, thus after the aluminium, you are having this oxygen. So oxygen is in the vicinity of this aluminium, so you need to put an oxygen over there. So you will put the oxygen here. Okay, and this was your pH. I hope this is quite clear to you. Rest of the hydrogens are quite clear. See, 2 hydrogens, sorry, here 2 hydrogens here, and 2 hydrogens here, and 1 hydrogen is here, which is connected with this one aluminium. Okay, this is quite simple. Now what will happen here? You are having you are having another molecule. This was your one of the hydrogen from this species will attack onto this one, and this will go there. The reaction is exactly the same reaction which we have done for in the first step. Now what will happen in the see, this is the step number 1. I am writing here step number 1. Okay, in the step number 1, the hydride is coming from this aluminium part and attacking onto this particular alpha carbon, and this negative charge now will attack onto this aluminium. Okay, this will attack onto this aluminium. So what I can do, I can write like that. This will attack onto the aluminium. So these 2 steps will occur in that. Now we'll connect with this second molecule. This is double bond, this is H, and it left with 1 hydrogen only. See, let me explain what is happening here. This aluminium now connected with this carbon. So this is the carbon, and that carbon you see is having phenyl group here, okay, which I have connected here, and then this part and that part. So this I have made this, okay. And then what will happen, the same step will go on. This hydride will attack onto this particular one and this will go up, okay. So what will happen in the next step, I'm writing here aluminium, and that this is your 5-membered ring, which is oxygen, in which oxygen is here. This is your phenyl part, this is your oxygen with negative, and this is having pH part. I hope this is quite clear to you, right? This has shifted onto this one here, you see, this will come here. I am writing that hydrogen with this yellow color, right, which actually comes from this part, and it is connected here. And second, it will go up, so this is where this one, and one hydrogen is already present here. And finally what will happen, this will attack onto the aluminium. So when this will attack onto the aluminium, what you will have, just like that, okay. So this is negatively charged, and of course lithium positive would also be there. And then finally you will do the protic workup for this one, that is H positive, and your aluminium hydroxide AlOH whole thrice will remove from here. And now you see you are having one of this system and second one of this system, two of the molecules you have used in the reaction. So this will gets converted into the alcohol, okay. So this is how you can produce, you can reduce that double bond as well. Now let's do the sum of the practice problems. What will happen in that case? Say this is your species. So I'm taking lithium aluminium hydride here. So if you are taking the lithium aluminium hydride, H3 I am writing, and one of the hydrogen I am writing in that manner because I needed this hydrogen to actually reduce that particular center. Please remember, okay. So it is not a good idea to put a star over there because star generally used for the stereo center, right? So this hydride will go there, okay. So how? Just like that, okay. And this will go up, okay. And when this will go up, you will have this particular species, for example. And if you notice onto this one, so this is basically the pre-existing stereo center onto this particular molecule. And when you do the protic workup, right, when you do the protic workup, so you will have this species. So this was your pre-existing chiral center in the molecule, and you have produced another chiral center here. That means the reaction is actually di-stereoselective. It's the stereoselective reaction. What happens in the stereoselective reaction? In the stereoselective reactions, you have the two different kinds of the stereoisomers. They can be enantiomers. If they are enantiomers, then it is enantioselective reactions. If they are the distereomers, then it is the distereoselective reactions. And from the basics of the stereochemistry, especially the dynamic stereochemistry, you know, when one stereo center is already present on the system and you are producing another stereo center, so that means definitely your distereomer will form. So when the distereomer will form, so we can have the two products. So I can write these two products separately here again. So say for example, my one product is, say for example, this is R, okay, this is also R. This remain unchanged in the reaction, this is R, and this would be S. So basically these two are the distereomers. What is the basic definition of the distereomers? When only, see, in one isomer you are having the two stereo centers which have the configuration just like that. So when in the next product only one stereo center is changing, then definitely it shows the distereomer relationship. This actually your major one, and 72% of this will form, and this is 28%. And how we can predict the concentration of the major and the minor product? For this you will use the Cramps rule. So I'm not going to discuss this Cramps rule here, because for the Cram's rules, right, and anti-Cram's rule, modified Cram rule, Franklin model, I have already uploaded the video. If you haven't seen those videos, I am giving you the link in the description box. You can learn the Cram rules and the Falcon and model to understand the percentage of this compound. Okay, it is very important to learn the Cram's model and Falcon N model to know the percentage of these major and the minor isomers. This is something very important. So stereochemistry also playing a very important part here. Now moving to the next one. Now this is the problem you can see here. One chiral center is already present here and another chiral center you will produce here. Again distereoselective reaction would be there and you will form the two different products, and again the percentage of the major and the minor product you can predict with the help of the Cramp rule. So what you do, say I am straightforward writing the product. So I am first of all, the hydrogen actually which comes from this lithium aluminium hydride will attach onto this carbon, electrophilic carbon, and this hydrogen will attach onto this one producing the alcohol. So you are having the two species. Again you see I am writing the structure of the two species very quickly. And rest, this one is the major one, 80%. Again you can predict the outcome of the reaction with the help of the Cram's model. Okay, this is very important, very important. Okay, now suppose you are having this particular compound and you want to reduce this particular compound with the help of the lithium aluminium hydride. Of course you will do the protic workup. Since it is the carbonyl compound, definitely it will convert into the alcohol. Okay, this will convert into the alcohol. So straightforward, what I can do, major product, 90% of this will form, only 10% of this will form. Okay, so for this let's check the reaction how we can do. So for this we need to convert this into the proper conformation. So 6-membered ring is very stable in the chair conformer. So this is chair. Okay, and I am putting my double bond here, no problem in that, and in the equatorial position I am giving this tertiary butyl group. Say this is your 1, this is 2, this is 3, this is 4, this is 5, this is 6. Similarly this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. You see here at position number 1 carbonyl is present, at position number 4 your tertiary butyl group is there. So I have intentionally put this group onto this equatorial position because this is the most stable conformation. You cannot put this on the axial position because in the axial position this will not be the very stable one. So believe me, it is the most stable form of this one. Okay, so what will happen here, you see, and this will attack onto this carbon. It is quite clear to you. So why actually it is happening here, you see, this hydrogen is your equatorial hydrogen which is present on the carbon number 2, and this is your axial hydrogen which is going down. So it can attack on the top, from the top. So when there is no steric hindrance here, so this will come here, this will go there. Okay, and then you are having which is attacking from the top and pushing this O negative here, just like that. There is no problem in that. Okay, and then you will do the protic workup. So this is your major product and you can very easily convert this into your species. You see here, so what I can do, I can delete this. You see here, this OH is actually the below the plane. That means it is alpha. It is alpha. Okay, and this hydrogen is the beta hydrogen. And you see, in this particular isomer which is 90%, you see this OH is your alpha. That means below the plane, and this H is your which is above the plane, which is your beta. Same relationship you are having. So you can convert this if you want, then you can convert this, make this 6-membered ring, okay, and put this OH below the plane, and then put this hydrogen above the plane, and then this one. So this was your major product, okay. And please, you should note this particular point, why actually it is happening. This actually ketone, which is your starting material, is unhindered. There is no steric hindrance here. For see, this will attack from here. See, it cannot attack from the bottom of the plane. Why? Then there occurs the interaction between the repulsion between this hydrogen and the attacking nucleophile. But here you see this space is empty, so it can easily attack onto this one. So your unhindered ketones, whenever you are having this unhindered ketones, your hydride donor, and your hydride donor is smaller. Please remember, this lithium aluminium hydride is low molecular weight and small in size as well. So when these two conditions met, your unhindered ketone and your small nucleophile, then always your H negative ion will occupy the axial position, okay, and alcohol will acquire in the will go to the equatorial position. So your equatorial alcohol will be the major product. This is very important, serious outcome of this one. So I am writing equatorial, I am writing equatorial, and this is axial. Very important one, right? You should remember this point. I hope this is quite clear to you. Now suppose you are having this species. So again what you can do, you can again make the two different isomers. So I am, first of all, I am writing the isomers. Most stable conformer. Say this one, and say this is 1, this is 2, this is 3, this is 4, this is 5, this is carbon number 6. Say this is 1, 1, 2, 3, 4, 5 and 6. So you see your 6 is your 5 is having, your carbon number 5 is having two methyl groups, one actually alpha above the plane, below the plane, and second is beta above the plane. So I can write my methyls like that. At carbon number 5, this is my first Me, and then my equatorial one, this is Me, okay. And at position number 3 you are having this one beta below the plane, so you can write like that, okay. See, since it is alpha below the plane, so it should also be alpha below the plane, right? This is your beta, so this is your beta, this is alpha, this is alpha. This is the most stable conformer of this one. I hope this is quite clear to you. Now what you can do here, you can do the same reaction. If this try to attack on the above side, so this methyl actually will repel this hydrogen, so this is the hindered ketone. So condition is not actually matching pretty quietly. So what will happen in that case? The only side which is left for this nucleophile, it will attack from the bottom of the plane, not the top of the plane, okay. So what will happen in that case? Then you will have your product, and this is H, and this oxygen is up, which is negatively charged. Since it is attacking from the bottom side, so it will acquire the equatorial position, pushing this oxygen onto the axial position, right? So this is axial oxygen now. So if you do the protic workup, so this will grab this one, and when this will grab this one, then you will have this product. So now this alcohol is what? Axial, and this is your equatorial. So result is different for this particular reaction. See, in the last reaction what you have seen here, your alcohol was equatorial, but in this particular reaction your alcohol is axial. When you have the hindered ketone, then your major product would be the alcohol which is present on the axial position, OH. However, the percentage of this one is not very high, only 55% of this you will get, okay. So if you want, then you can convert this into this form, in this form. How we can convert in this form? Very quickly, you make this Okay, now you see here your alcohol is above the plane. Okay, so when it is above the plane, so you can write OH, and you see this H is below the plane. So what you will do here, you will put this H below the plane. Next is quite fine. Okay, methyls and other systems are also there. Mm, mm, mm. At position number 3 here, this is at the bottom of the plane, and here bottom of the plane is above the plane. So this is the major product. Okay, and you see this OH here, there, this is the major product. Okay, so basically these are equivalent. So in case of the hindered ketone, you will form the alcohol which is equatorial, and in case of the unhindered ketone, you will have the alcohol which occupies the equatorial position. This is the very important outcome. I hope this is quite clear to you. So variety of the problems are actually there, and see what you can do. If you increase the size of this nucleophile, if you increase the size of this nucleophile, then reaction goes in the pretty different manner. Now suppose what you can do the same reaction with the, say for example, if you use a very bulky or a very heavy nucleophile, nucleophile, or you say the hydride ion, this is Al O tertiary butoxy, okay, and this is hydrogen, 3 times are present. So this particular product, the concentration will increase by 99%. Because see, this is bulky in nature, it will react very slowly, and when it will react very slowly, it is very selective. It is very highly selective, so that it can produce that axial alcohol into in this particular concentration, 99%. Okay, when you have the hindered ketone, very bulky, your attacking reagent, then axial alcohol will form in the very high amount, that is in the 99%. I hope this is quite clear to you. Okay, so there are number of problems you can solve using this particular method. Okay, now this is your another species. Again, the same reaction you can do. See, you can put OH here and H here, alcohol you will produce, and this is quite bulky here. Very bulky group is there, right? Since it is very bulky group is there, and it is quite clear your axial alcohol will form in that case, where in the major amount. Okay, so I am leaving this problem to you. Solve this particular problem, and if you find the answer, then it is quite good. If you are not able to write the reaction for this one, you can come back to the comment section, so that I can explain this problem as well. Okay, this is my next problem, and this is problem number, it should be problem number 6. Okay, I made a mistake here, and this is simply the decalin system, and this decalin system is having your carbonyl functionality. So what you can do, first of all, you can do you can write the proper conformation of this one, just like that. Two 6-membered rings are fused here, so I am writing this one like that, right? Okay, and you see this hydrogen is your beta hydrogen, that is above the plane. So I am placing this hydrogen here just like that. H I am putting, and this hydrogen is the alpha, that means below the plane. So I am putting this H below the plane. Okay, and here you see you are having the carbonyl functionality. This is how you can draw this one. Okay, and this is my axial hydrogen which is below the plane. This is my equatorial hydrogen, this is above the plane. Okay, attack onto this one from the top side. Why top side? See, it can also, if you want, then you can try this as well, below the plane. So when it when it goes below the plane, so it will have the repulsion. Okay, because this hydrogen is there. Okay, and this hydrogen is here, but here you see this is more accessible, this part is more accessible, A is more feasible, so it is attacking on from the top. So when it is attacking from the top, that means hydrogen will go to the axial position, and OH will go to will come to the equatorial position. Again you see you will have OH is down, just like that. Okay, you will form this particular product. Okay, and if you want, then you can convert this into the desired simple 6-membered ring. So this hydrogen was above the plane, this was here below the plane. Okay, and here you see your hydrogen is above the plane and your OH is below the plane. As you can see here, this is below the plane, equatorial, this is below the plane. So this is how you can write the reaction for this one as well. Okay, so this is something very, very important, very, very important. Now next, okay, this problem is again quite easy, and you have to decide what is happening in that case. Okay, say for example, uh, you are doing this reaction and pyridine is the solvent here in that case. So what product you are going to form? Of course, alcohol will not form in that case, because you are not doing the protic workup, you are taking your acetic anhydride in that case. Okay, so that means acetyl functionality will be introduced onto this particular carbon. Okay, and if you want, then you can very quickly write the, say for example, for this one, what is the conformation? Right, like that. Okay, and say this is your oxygen. So what I am doing here, 1, 2, 3, 4, 5 and 6, this I have written over there. Okay, and you see now you can number this as well. Say this is your 1, this is 2, this is 3, this is 4, this is 5, this is 6, and at position number 2 you are having this system. So I am writing this with this one. This at position number 2, this bond is here, and this bond is having NH here, and after NH you are having your another carbonyl functionality, and after the carbonyl functionality it is connected with the carbon number 3. So I have drawn it correctly actually, right? You see this position number 2, this is position number 2, it is having the NH group, this NH group is here. Position number 3 is having this bond and this carbonyl functionality, this I have drawn in that manner. Okay, now it is quite easy to see, it cannot attack from the top, it cannot attack from the top. Why? Because this is the steric hindrance which will be produced by this 5-membered ring, which contains your amide functionality, right? This is your amide functionality, cyclic amide. Okay, so this will not attack from here. The only possible way for this is what? It will attack from the bottom of the plane. That means this hydrogen will acquire equatorial position, pushing this oxygen to the axial position. So your product would be like that, not product actually, your intermediate would be like that. And then in the next step you are having your CH3. So what will happen in that case? This one, okay, will be grabbed by this proton. So your product would look like O, C double bond O, CH3, and the equatorial position you are having the hydrogen. This will be the product. And next problem you see, okay, this is another very, very special problem, very important problem. You see this phase is the endophase and this is your exophase. Okay, please remember, you see, whenever this phase actually, which is actually here on the left hand side of this one, this is your endophase, please remember. Okay, and the above one is the exophase, and then you are attacking this with the lithium aluminium hydride. So from which phase it will attack, exophase or the endophase? This will attack from the exophase because it is unhindered. Okay, and it will push this oxygen onto this particular position, and your alcohol generally acquires the axial position. So what will be the product? Hydrogen is here, OH is down, and 89% of this you will form. Remaining 11% would be the isomer, where OH would be the equatorial and H would be the axial type of thing. But if I change this, right, this one, see what I have done here. See, initially there were no groups present on this bridgehead position as well as on this particular position, but in my new problem I have introduced these two here and one here. So what will happen here? You see, due to this one from the endo phase, this is more acceptable, and this cannot attack from here because these are the methyl groups, hydrogen, hydrogen and hydrogen here, and this again H, H and H. So due to this steric hindrance, this exophase is not a very good idea for this hydride to approach. So it is going bottom of the plane, pushing this alcohol onto the equatorial position, and hydrogen will come into the axial type of the position, and you will have your product. So this actually changed the course of the reaction, and 92% of this will form. So carbonyl chemistry is very important chemistry. Okay, now see, it is very important now, very important one. Why it is important? You see, this triple bond is generally not reduced by the lithium aluminium hydride, but when it is in conjugation with this benzene ring, then you can reduce this particular bond to the double bond. Very important reaction, and it will give you the very what you can say, the stereoselective reaction, because E alkenes, enters as in alkene will form in that case. So it is very important to note that lithium aluminium hydride does not reduce this triple bond, but in case of this your propagylic alcohols, I know you know, where alcohol is present along with the triple bond, right? When alcohol and triple bond is present together in this in the molecule, then it is known as the propagylic alcohol. When this happens actually, then this double bond can be reduced to the double bond, giving you the E alkenes, stereoselective reactions. Okay, so your product would be just like that. Benzene ring, there is no problem in that. And then C double bond C, one hydrogen is above, second hydrogen is here, and already you are having this alcohol, which is this one. Okay, and you see this hydrogen and this hydrogen, they are having the anti-relationship, so this is E alkene. This can be reduced, and when this will happen only when you have the OH functionality and triple bond present together, or OME and triple bond together. This will happen only, okay, when these two situations met. So again you see the same reaction. This will what? Carbon double bond carbon, one hydrogen will go up, another hydrogen will come down. Okay, there is no problem in that. And this is your OME type of thing. This is H, this is H, again E alkene is produced. Okay, but you see this in both the cases, the temperature condition of this reaction is very low, minus 78 degrees centigrade, and this will also happen at minus 78 degrees centigrade. These are the very important reactions. Okay, now reductions of the acid and the acid derivatives, this I have already told you, you can reduce any acid or the any acid derivative. So very quickly what you can see, we can, this is your benzene ring, CH double bond, CHCOOH, suppose this is your acid. Okay, and you are doing the reaction here with the help of the lithium aluminium hydride. So I am quickly writing the reaction. Okay, so what will happen in that case, because this double bond is in conjugation with this benzene ring, so this will also gets reduced along with the acid, you know, when reduced strongly with the help of the lithium aluminium hydride, so it will form the alcohol. So you will have this particular product, this one, this is your CH2, this is your CH2, and this is your CH2OH. Alcohol will form. Okay, no problem in that. And if you have the ester, suppose, say for example, you are having this species, C double bond O, OC2H5. and you are doing the same reaction, LAH. So it will also reduce to the alcohol, benzene ring, and this will become CH2OH. Okay, and then another alcohol will be there, which would be your C2H5OH. And similarly, if you have the acid amide, right, amide, CONH2, acid amide, and if you want to reduce this, I already told you, amide will form what? Amide will form amines. So this will be a CH3, this is CH2, this is NH2 again. Okay, that means H2O will be gone from here. So as I already told you, acid and acid derivatives will form alcohols, amides will form amines. Okay, so there are number of reactions of this type. And then your reduction of the epoxide and the ozonides. Again, it is quite simple one. Say for example, this is my R CH CH2, and this is my oxygen which is connected with this one. Or if I want to reduce this with lithium aluminium hydride and I do the protonation of this one, then again I'll produce my alcohol, which is your CH. This will CH3 now, this is OH. Please remember, this hydrogen will go to any of the carbon, okay, and this proton, this will come here. Alcohol you have produced, right? So this is your epoxide, okay, epoxide. Cyclic ethers are epoxide, you know, okay. And when you have the ozonides, say for example, what we can do for ozonide, say for example you are having this one, say this is your CH3, and say this is CH2 3 times, CH3, and say this is your CH double bond CH3, right? This is your alkene, and you do the ozonolysis for this one, so this is ozone. So what you will have, CH3 CH2 times 3, this is your CH oxygen, and this is your CH and CH3, okay, and then oxygen, this is your ozonide, okay. So when you reduce this ozonide with the help of the lithium aluminium hydride, you will get this alcohol, CH3 CH2 3 times, and then CH2OH. I hope you know what is this. This is your amyl alcohol, amyl alcohol, N-amyl alcohol. Normal it is because straight chain is there. This is how you can do. Next is the nitro compounds. Okay, nitro compounds, aliphatic nitro compounds. First of all, this is important reaction for you. I am doing aliphatic nitro compounds, and in the second slide of my lecture, I told you your aliphatic nitro compound, when reduced with the help of the lithium aluminium hydride, it will form amines. Okay, so I am doing for the aliphatic nitro compound. Say this is your CH3, this is CH, this is NO2 again, and this is CH2, this is CH3, and you are reducing it with the LAH, that is lithium aluminium hydride. Then you will have CH NH2, okay, and then CH2 CH3, aniline, right, secondary amine you are producing here, and of course 2H2O will be removed from here. Now suppose you are having aromatic, very important one, especially for the JEE examination. You are having the aromatic nitro compounds. Say you are having nitrobenzene, okay. So what you see, if you do the reaction of this nitrobenzene with this lithium aluminium hydride, in the mixture you are having the two products initially. First is your nitrosobenzene, which is your NO, C6H5NO, and then you are having C6H5NHOH, this one, right? When these two present in the mixture all together, water molecule will be removed from here, this H2O molecule, and then you are having C6H5 over there with nitrogen and oxygen, and in the bottom you are having C6H5, N is there and they gets connected. Okay, this is azoxybenzene. What? This is your azoxybenzene. When you reduce this with LAH, then you will form azobenzene. C6H5N double bond N, C6H5 plus H2O. This is your azobenzene. This is your azobenzene. Okay, very important reaction. And like your carbonyl compounds, these nitriles are very, very important when it comes to the lithium aluminium hydride chemistry. When you want to reduce these nitriles, then of course your amines will form, and this is very, very important reaction, frequently used in the organic synthesis. Reduction of the nitriles with the help of the lithium aluminium hydride. So what you can do? See, why this reaction is very, very important. So I am writing condition 1. I am writing condition 1. So what is condition 1? When your nitrile is small, in a small amount, when nitriles are added to LAH, means it is in excess and it is in small quantity. When this condition happens, so what will happen in that case? Say you are having cyanobenzene, carbon triple bond nitrogen, and you are doing this reaction with the LAH. So you will produce the aliphatic amine, CH2 and NH2. Okay, it is present in the excess. And second condition, I am writing here, condition 2. What is condition 2? When LAH, lithium aluminium hydride, is added to nitriles. That means nitriles is in excess and LAH is in the small quantity. So when this happens, say for example R, C triple bond N, okay, and you are doing this reaction with this LAH. So first you will produce this imine, double bond in the amine, that is imine, and if you do the protic workup, that is HOH, then you will have aldehyde along with the liberation of the ammonia. So these two reactions are very, very important reactions. Let's see what's next. Okay, reduction of analytes. So how the analytes can be reduced? So I'm taking the example of the acid analyte. Say this is the benzene ring and this is my NHCOCH3. This is my acid analyte. And when I reduce my acid analyte with this reagent, it will get converted into the amines. Okay, NH, this is CH2 and this is CH3. 2-degree amine you are producing here. 2-degree amines. Okay. And then the reduction of this is probably this is your last reaction, reduction of the sulfur compounds. Okay. Say for example, you are having RSO2Cl, sulfonyl chloride. Okay. Alkyl sulfonyl chloride, and you are reducing this with the LAH. So it will form thiol. So this is your thiol. Okay. And when you have R2SO type of compound, you are doing the same reaction. Then you have thioether. This compound is thioether. Okay. And see, variety of reactions are there. Variety of reactions are there. I hope this much of information is quite enough to understand the role of the lithium aluminium hydride in the pretty much detail. So the length of the lecture is very, very what you can say, the lengthy lecture it is. Okay, but this lecture will be very, very useful for all of you, whether you are CSI or NET aspirants or GATE or IIT JAM aspirants, or you are preparing for your IIT JAM or NEET examination, this information is very, very important. Okay, so I hope you understood the things well. And if you understood the things well, please give thumbs up to my lecture. And if you're watching video for the first time, please subscribe the Tetrahedron Chemistry classes. Okay, that's it for today. Thank you very much.